So let's look at the delayed impulse. We've seen that we can write the delayed impulse in time as delta t minus tau. So that's going to delay that impulse by a factor of tau. So we've got it drawn here. Now if we were working out the Fourier transform of that, we would take the integral from minus infinity to infinity of our function delta t minus tau, multiply e to the minus I omega t by dt. Now we've seen from the shifting property that this is simply going to be equal to 1 times e to the minus I omega tau. So the Fourier transform of delta t minus tau will be e to the minus I omega tau. So that's the transform pair. So that's really telling us that if we were to delay a function in time, it's equivalent to adding linear phase on in frequency. Now we can do the same thing in the frequency axis. Instead of drawing the impulse in the time domain, if the impulse now exists in the frequency domain, then we would be taking a delta omega and delaying it by some factor v. So this little function here is delta omega minus v. Now what we can do is we can work out the inverse transform of this. So the inverse transform of it is going to be 1 upon 2 pi the integral from minus infinity to infinity of our function delta omega minus v times e to minus I omega t by d omega. Again, the same as previously, via the shifting property, we can see that's going to be e to the ivt times 1 upon 2 pi. So we can then take the 2 pi to the other side and we'll be left with the Fourier transform of e to the ivt would be equal to 2 pi delta omega minus v. So we can say that if we were to delay an impulse in the frequency domain, this will give us a linear phase change in the time domain. Now we're not actually going to be using this here because this is introducing complex valued functions of time and we're not really going to be dealing with those in this course. So let's look at a summary of 4 of the transform pairs we've got from impulses. So we've seen that delta t gives us a value of 1. We've seen that 1 gives a value of 2 pi delta omega. And now we've seen that delta t minus tau, this is the delayed version, gives us e to the minus I omega tau. And in the frequency domain, we can say that a delayed impulse in the frequency domain will give us a value of e to the ivt, which is a linear phase addition in the time domain. So let's look at the delayed impulse in MATLAB. So if we had the impulse function, I've got it down here below, that's a value of delta t. When we do the Fourier transform of it, we get this function here which is the value of 1 across the entire frequency spectrum. And I've drawn these little lines up just to represent individual phasors. So let's go and we'll look and see what happens whenever we delay this in MATLAB. So this is the delayed version here. We've taken our delta t and we've delayed it by a value tau1. So you can see that this straight line that we had along the real axis is starting to bend and curve. That is, the phasors are starting to rotate, and you can see this rotation starting here. So let's look at and see what happens when we delay it. We add in an extra delay. So here we've delayed it by a value of tau2, and you can see that the whole of this graph here is starting to corkscrew around the complex plane. So let's have a look at these actually within the MATLAB code. So we're going to use this file f1.m. You have access to that in the resources section. So we're going to use a delayed impulse. So the impulse function in MATLAB is the Dirac, so it's called Dirac and it's the time, and we're going to delay this by 0.5 and we'll do it from limits minus 10 to 10. So you note that whenever you put a function in to this f1, you have to put the function within quotes. So you see 2 little quotes, one either side. So let's go ahead and we'll run that and we'll see what we get. So that's the output here. The input is the function f of t, which is the delayed impulse. It doesn't quite show you here, but it is delayed by a small amount. And in the top line here is the output. So the output there, you can see normally if the impulse function had been at 0, then it would just be a straight line across at height 1. But now all of the phasors in effect have started to rotate, and you can see that rotation here shown. Now what you could do is you could go and change the value from 0.5 and put different values in and try it yourself and see what happens. So the more you delay it, the more the delay is added in here, the greater the phase shift in the frequency domain. So that's us finished with our introduction to the impulse function. There's quite a lot in the last video and this video, but it's a really useful function, and we'll see it cropping up through the rest of the video series. So thank you for listening. I'll get you in the next video. Goodbye.